All right, so that is the regression setup. So for every x, we've got a whole distribution of the y's. Look at the mean. Another x, look at the mean of the y's, and then join them up, and that's the straight line, and so on. But very often, we can't afford to run an experiment that way. We can't afford to fix an x and get a whole bunch of y's and get a mean, or fix another x and get a mean, and then fit a straight line. And even if we could, those points may not lie on a straight line because of random sampling, experimental error, what have you. Okay, so now we would like to look at this generic problem where we have points through which we would like to fit a straight line. So here's an example. So what they did with this article is they looked at people who have been diagnosed with, this is what they used to call type 2 diabetes, the NIDDM, non-insulin dependent diabetes mellitus. And so this study was actually done in 2 countries, in Australia and in the US. And what these points here, so what they did is they looked at people who have been diagnosed for a certain number of years post-diagnosis with NIDDM, or type 2 diabetes, and then they looked at a retinopathy. So what percent of these people had retinopathy? And so these dots here, I think this one belongs here, but anyway, these dots here, I believe, are the US numbers, and these are the Australian numbers. But what you notice is that here we get the clinical diagnosis. So here's the clinical diagnosis, that's the origin, that's the 0. And then all of a sudden, the next day, you have this percent with retinopathy. Same thing happens with even higher in Australia. Doesn't make sense. It doesn't make sense that you go the day you diagnosed, or this doesn't make sense at all. That there's nothing going on down here. There are no points down there. Well, of course, there's no point down there because they haven't been diagnosed. So this is the diagnosis point. But should they have been diagnosed? Okay. So their argument is that these people are being missed. There are some people, these people here, they're being missed. They're not being diagnosed properly. And that this NIDDM is not a benign condition. In fact, it's churning away and doing damage even before it gets diagnosed. So the subclinical manifestation of NIDDM is what they're trying to look at here. And they're arguing that, once again, nature likes to be smooth. So maybe there's that straight line, and if we extend that straight line beyond our experimental region, it's always dangerous to go beyond the experimental region, but if we do that, then they estimate that this group, in fact, maybe have had diabetes for the last 6.5 years or so. This group here is, in fact, 4.2 years. So generically, what we're talking about here is, here's a bunch of points, and we'd like to put a straight line through them because we feel that that would be a smoother interpretation of what's going on. Okay? If we were able to observe more data, maybe these points all would cluster around the straight line more tightly and all that. The usual arguments that we can best estimate the mean if we have a large number of observations. This is just a manifestation of the same idea. But generically, as I said, we can look at this as trying to fit a straight line through some points. And this I find a very interesting application. So here are the head circumferences for some of these babies. These premature babies we were looking at earlier. All right? And as a function of gestational age. There's actually more than 100 there, but they're all falling on the same point, and so you just see one little circle. All right, but it doesn't matter. Somehow, what we could do as I said, what we could do is we could look at the mean of these points and come up with their average as it would get a mean like this. And then get the mean of these points, and it might get a point like this. And the mean of those points might be here, and so on. And then say, all right, there are points who are on my regression line. And so here's one here, and then this one here. But the point is that you're not going to get a regression line going through those points because, they're all over the place. Plus, this is based on 2 points, this is based on 2 points, this is based on a whole bunch of points. So maybe we should trust this one a little bit more than that one or that one. Okay, so things get a little bit more complex. But anyway, so let's ignore that and let's just say, all right, let's just treat all these points as if they are equally accurate, and we just have these points. Let me fit a straight line through these points, and then I'll use that as my regression line. So here's the question. What line, there's an infinite number of lines I could put through these points. What line should I choose to represent these points? For example, should I choose that line? You might say, oh, no, that's terrible. You're not representing these guys down here. You got them up there. And these guys up here, you got them down here. So, no. That's terrible. So, no, let's not do that. You'd rather see something that does something like that. That's better representation. In fact, I might even do something closer. I might get something like that. That's even better. I agree. That is better. But can we find an objective way of comparing these two lines so that we can say, oh, I prefer this line to that line because this line has such and such a property and that line doesn't have such a property? What we can do is for every time we draw a line through there, we can ask how close is that line to each one of these points. So for example, here, that point lies on the line. So perfect. So the distance is 0. What about this point? Well, this point is yay much away from the line. What about this point? It's almost on the line. This point is yay much away. This point is that much away. This point is that much away. For each point, we can take the vertical distance of the point to the line. Ideally, we'd love to make all those distances equal to 0. We can't. We can only do that if the points actually lie on a straight line, which they don't. Obviously, they don't. Right. So we can't do that. So what can we do? Well, what happens is it's the same problem we had with the variance. We can take the sum of all these points and put those points and minimize the sum of that. Well, it turns out that as long as the points go through the mean, suppose this point is, so these are the x's, these are the y's, so suppose that point is equal to x bar, y bar, then any line that goes through that point, so including this line, that line, that line, that line, any line that goes through those points will have 0 for the sum of all these distances. These distances are called residuals. So any line that goes through the center of gravity will have 0 sum for the residuals. So what did we say when we discovered this, when we were doing the variances? Well, first thing we said was, well, get rid of the signs. So look at the absolute distances. You see here what happens is the positive ones cancel out the negative ones. So look at the absolute values. So here's, for example, E1 through E7. Look at the absolute values of those residuals and make that as small as you can. And that was the brilliant idea of one Ruggero Giuseppe Boscovich. And he was trying to estimate the distance to the moon, I believe, when he came up with this idea. Brilliant idea. And not only that, he showed us how to actually calculate. So he said, okay, here's a line, and I'm going to give you the alpha and your beta, and you're going to predict your y's with that. And I'm going to do it in such a way that you take the absolute value of y minus beta x and take that sum over all, so you have points j, j, j equals 1 to n. And I'll tell you how to calculate alpha and beta. You give me the xj pair, xj, yj pairs, and I'll give you the alpha. He had a brilliant algorithm to do this. The only problem with that was that there's nothing wrong with it. It was wonderful. The only problem is that it was difficult to extend to more than one variable. In fact, virtually impossible to do that. And absolute values in mathematics are just, they're not lovely things to deal with. But anyway, so this idea was kind of abandoned so this is Boscovich's idea, and this was abandoned when Gauss came along. Remember Gauss? I said we looked at this Deutsche Mark because of the normal curve. But actually what he did do is he said to us, okay, look at those residuals, and now instead of taking the sum of the residuals, which is always 0 if it goes through the center of gravity, he says, all right, take the least squares line. And now the least squares line is the line which minimizes the sum of the squares of the residuals. So he got rid of the sign by squaring each one of the residuals. All right? So this is what is called least squares. So this is the line that's least squares, the line of least squares. And it's got all sorts of wonderful properties, and not the least of which is we know how to calculate it, and rather easily. He came up with the formulas for calculating this, and it was very, very nice. And this is what Stater does for us and everything. So this is the least squares line. So the difference between the least squares line, they both the Boscovich and the Gauss both go through x bar, y bar, but the difference is that the least squares one minimizes the sums of squares of the residuals. Now, this is also actually, it's a little bit of a shortcoming, because if you look at this, this means that every distance is squared. So big distances are given even more emphasis. So it turns out the least squares line is impacted, unfortunately, by residuals that are very large. You will see that for yourself when you try and play with this later. So here's an example. So here's that data set I showed you, except this is the first 15 or so of those data sets. So here's the head circumference, and here's the length of the baby. Well, it's like height, but you know, the baby's lying down. The baby can't stand up. So the baby's lying down, so they call it the length. And then there's the weights in grams, and toxemia, whether the mother had toxemia or not, mother's age, and so on. Systolic blood pressure, the sex of the baby. Now, then we get to germinal matrix hemorrhaging, and then there's the gestational age, and there's the APGAR score. Okay, so there's our data set. And so very simply, here is a plot of the head circumference versus birth weight. So you can see that it looks pretty linear. Okay, so there's a scatter plot. Now, you may have noticed that in the corner, I did a jitter, what's called a jitter. It's because these observations fall on top of each other. And so rather than get a picture that looks like this, where it looks like you don't have too many observations, in fact, what you do is they tell you you ask Stater to jitter. So there it is. It's not jotter, it's jitter. And what it does is it just jitters the observation, just a smidgen, so that they don't lie on top of each other and look like one. They separate it so you can see that there's 2 or 3 or 4 falling on that point. Anyway, so this is a better reflection of what's really going on, how many observations you have. And this looks pretty linear. So then, here's the Stater command. You say regress. Head circumference. On what? Gestational age. And that's it. Simple. What Stater then does is it calculates the least squares line for you. All right? The Gauss idea of least squares line. The line that minimizes the sums of squares of these residuals. And here it is. And the way we read this is, all right, there's 100 data points, and then here are the variables that we're looking at. Gestational age. So here's the one on the left-hand side is head circumference. Then we're going to look at gestational age and the constant. So there's the constant term. We usually ignore the constant term. So anyway, so we see that the coefficient, here are the coefficients of the least squares line. So there is the least squares line. The least squares line is that head circumference is 3.914, that's this one, that's the constant, plus 0.78, that's this one, times gestational age, plus some error term. And that's the residual. So there is the least squares line. It tells us that head circumference increases by 0.78 every week of gestational age increase. The head circumference increases by 0.78 centimeters. And this is the intercept, although intercept means nothing here because our experimental region, most of these babies are 26, 27, 28, 29 weeks. So a zero gestational age doesn't make any sense. We're way beyond our experimental region. So we don't want to do that. We're just assuming linearity within our experimental region. So we look at gestational age and we look at where we are in the experiment. And this is a good general advice. Be very careful when you extend yourself beyond the experimental region. Okay. Now, not only that, we look up here and we see something called root mean squared error. So it's the square root of the mean squared error, and that is our estimate of the standard deviation. So the estimate of the standard deviation is 1.59. And here's the standard error of the estimate of the coefficient, and there's our t, and there's our p-value. So our p-value says that p is 0.0000, and so less than 0.0005, and so we would reject the null hypothesis that the beta related to gestational age is equal to 0. So we reject that hypothesis. We also could have done it with the confidence interval. There's the confidence interval. It's between 0.655 and 0.905. So we reject the null hypothesis that the beta is equal to 0. So in other words, we're saying, and it makes perfect sense, that the baby keeps on growing in utero. So the head circumference tends to be a little bit bigger if you get, if you wait another week or so. So that's what this says. Now the other one is the r squared. Remember I said to you r squared. So there's the r squared, but there's two r squareds here. There's the r squared and there's the adjusted r squared. I would recommend looking at the adjusted r squared. The adjusted r squared incorporates adding more covariates. We'll come to that in a minute. We're talking about simple linear regression now. So there it is. Those are the important things to get from this.